cute little KCET 2026 champions, welcome back to Sankalp series, where we have taken a pledge that we will work harder and harder every single day to get you to top 1000 rank in 2026, right? So in today's class, we are going to start a brand new chapter, that is chapter number 3, Chemical Kinetics Part 1. Okay, so what all topics we are going to discuss in this particular chapter, I will let you know after some time. Okay, now before that, let's imagine a very beautiful scenario. Okay, let me take you to something that you will enjoy. Pizza race. Okay, what is this? Let us imagine that you all friends have met in a very beautiful Sunday evening to have party. Okay, now two of your friends started craving for pizza. Okay, so this friend and this friend started craving for pizza and they want to order pizza. Okay, so they have two outlets. There is one outlet A here and outlet B here. This friend wants to order from this outlet and this friend wants to order from this outlet. Now what will happen? Both of them place the order. Okay, so the delivery time for this one shows 15 minutes, whereas the delivery time for this one shows 40 minutes. I hope it is visible. This side it is 15 minutes and this side it is 40 minutes. Now a question arises in our mind that why this is very fast and why this is very slow when you have ordered the same size pizza, same city, same distance, then why is this the speed or the delivery time is different? You can very well see here that we have a huge traffic on this road, right? The same thing happens in chemical reactions. Certain chemical reactions are very slow, whereas certain chemical reactions are very fast, whereas certain chemical reactions have a moderate rate. Okay, so that is what in the spotlight today we are going to study about the speed of the reactions, the rate of the reactions. Okay, so now now just tell me what will happen, what worst can happen if the pizza gets delivered 40 minutes, like it becomes slow or it is a late. What will be your reaction? Just comment down and tell me. I can just imagine that if it happens in my case, I will be little bit more hungry, I will be more angry, I will be like moving here and there when the delivery will come. These all things will happen. Maximum, worst case, nothing much serious, right? But just imagine if the same thing happens in case of a life-saving drug. Okay, so let's move to a different scenario to understand what is the importance of the speed of the reactions. Let me just take you to a next scenario. So we are now, imagine that your favorite beloved JJ Mam is sick. Okay, she is not well, she is in hospital. Now I, as a true friend of her, has consulted the doctor, and Dr. Ankit sir has told me that we need one antidote to save JJ Mam. Okay, so this antidote can save JJ Mam, but here is something, the catch, that this antidote should be given to her within 24 hours. The clock is ticking now, right? Within 24 hours. And the worst situation is this antidote is not available in the shops or in the medical shops, right? So what I'll do, I'm very scared, but we cannot like what I'll say, we cannot just leave the situation like this. We have to fight back here. So I moved all the way to our very famous institute, ICMR, Indian Council of Medical Research. And do you know whom I met there? I met our favorite Somik sir there. Okay, and then I told every situation, described everything regarding JJ Mam to Somik sir. I told him that Somik sir, JJ Mam is not well and to save her, I need this antidote within 24 hours. Okay, then Somik sir is now very tensed and he said me that the antidote takes time to be prepared. Okay, it is very difficult to prepare that in 24 hours. Let me think. Okay, so now Somik sir has just put in all his knowledge, all his talent, all his science nature, everything in his brain is moving around. Can this is possible? If we can prepare this antidote within 24 hours, okay, can we save JJ Mam? So after thinking a lot, he gives me that I studied in chemical kinetics that the rate of the reaction can be increased by certain factors like concentration, temperature, catalyst. So a speed of the reaction is already there, but we can change the speed of the reaction by 3 factors: concentration, temperature and catalyst. And after analyzing everything, after putting all his knowledge into play, he gave me a confirmation that using this, I think I can prepare that antidote within 24 hours and we can save JJ Mam. Okay, so that is the thing here. Now Soumik sir is in the lab and he is preparing the antidote for us to save JJ Mam, and at the end of this chapter we will know whether we were able to save JJ Mam or not, and if yes, how could we do that, right? So now when Soumik sir is preparing the antidote in the lab, I will tell you the chemistry of chemical kinetics, right? So in today's class, what we are going to study? We are going to study about the rate of a chemical reaction. I already defined what is rate of a chemical reaction, speed of a chemical reaction. So that we will see. Then we will see some factors influencing the rate of the reaction. Okay, what all factors are there which affects the rate of the reaction? Already Soumik sir has told us, but I as a teacher will teach you again in detail. Next, integrated rate equation. What is this integrated rate equation? And this is going to be the main thing that will help us to prepare the antidote for JJ Mam and save her life. Okay, in the second part we will talk about the temperature dependence, effect of catalyst, and in the part 3 we will go for collision theory. Okay, so this is going to be the class today, and I hope all of you are super excited, and you don't worry, we will definitely try our best and save JJ Mam. So those who are ready to start this chapter, please put a thumbs up in the comment section with full energy, with full confidence. Let's move ahead. Okay, fine. So now let us understand something regarding chemical kinetics. I'll give you certain things. Have you observed them in your nature, in your house or in your environment, in your surrounding or not? Have you ever seen a bread getting spoiled like this, getting fungus on that, right? So what happens? How rapidly the food gets spoiled? If you imagine or if you think that suppose some milk is there, some curry is there, if it is a winter season, okay, if the atmosphere is cold, then this food do not get spoiled easily. Whereas if you leave it outside, okay, if you just leave it in a hot summer, at that case the food or the milk or anything gets spoiled easily. Okay, so what is the difference? Why there is certain things in certain temperature become slow? When the temperature increases, this rate of the reaction increases. So here we can understand how efficient or how important is the role of a temperature in the rate of the reaction. Then have you ever wondered this tooth? How many, now tell me something very, very important. How many of you have got any fillings in the tooth, or you have done root canal treatment of your teeth? I got recently, in very few days I have got it. So I know that they used to put, when I got filling and root canal both, and when they fill something, after few seconds the material gets set. Okay, it is a chemical reaction, but that is so fast, so quick, that within 1 hour they put the filling and then it is also set in our teeth. So have you ever wondered about that how to design a rapidly setting material for dental filling? What must be done? What must be the composition there, that the speed of the reaction is so fast that within 1 hour everything gets done here in the filling part. Okay, now have you imagined another situation where we have this? Can you imagine what is this? Actually I want to show you the fuel. Okay, the fuel and the engine and the fuel. So have you ever thought the mileage and all, where we check, right? When we go and buy any new vehicle, any new bike, you go and check the mileage. You do so much research about that. So what is it exactly? We are checking in this much amount of fuel, how much energy will be produced and how much distance we can cover, right? So that is also something. What controls the rate at which the fuel burns in an auto engine? Okay, so these all questions: how rapidly the food gets spoiled, how the material is designed so that the setting is so quick, how much distance we can cover by burning the fuel. This everything is answered by one branch of chemistry, and that is chemical kinetics. That is what we are going to discuss today. Okay, so now let's give you an introduction. Very basic introduction. I know by this time all of you are very familiar with chemical kinetics. So chemical kinetics is that branch of chemistry which deals with the study of reaction rates. Means how fast how slow the reaction takes place. Okay, so reaction rate study is called as chemical kinetics. Never forget this. Okay, I hope you will remember. So the mechanisms is called as chemical kinetics. Now what is second part we have? The word kinetics is derived from the Greek word kinesis, meaning movement. Okay, so when the movement is there, to denote that we have used this word. Okay, that is nothing for exam point of view, just for knowledge. Now listen, here's something very important. Thermodynamics and chemical kinetics, two important branch of chemistry. Thermodynamics and chemical kinetics. Thermodynamics will tell you whether a reaction will happen or not happen, right? You know, delta G is, if it is negative, the reaction will happen. Delta G, if it is positive, the reaction will not happen by its own. But chemical kinetics tells you that if the reaction is happening, how fast, how slow the reaction will take place. Now let me give you a very simple example. For example, if you know, thermodynamics tells us that diamond can be converted to carbon or graphite. Diamond can be converted to carbon or graphite, right? That is possible, or the reaction is feasible according to thermodynamics. But the rate of this reaction is very slow, is so slow that we assume that diamond, once it is prepared, it will remain permanently with us. But with thousands and thousands of years, this diamond will get converted to carbon or graphite. But we don't see that, right? Because the reaction rate is very slow, and that is why we assume that this diamond will remain as it is forever. Okay, so here is a beautiful example. The thermodynamics data indicate that diamond shall convert to graphite. Okay, but in reality the conversion rate is so slow that the change is not perceptible at all. Means we cannot see any difference in the diamond size, shape, its glow, anything, and we assume that the diamond is forever. But if you keep a diamond, if you have a diamond, you are very lucky if you have this, and if you keep it for thousands and thousands and thousands years, after that if you check, the diamond would have converted to graphite. But it is so slow that we don't observe in our regular life, right? Okay, so now after this brief introduction, I'll also give you an example. I told you certain reactions are very fast, certain reactions are very slow. So let us see one example here. So just a minute. Yep. So you can see this reaction. So now I told you that certain reactions are very fast, whereas certain reactions are very slow, right? Let us find out some examples for this. So I'll show you one reaction. So what exactly is happening? We have taken AgNO3 solution in this, okay, and then you are adding some NaCl to that, okay. Now you see, as soon as I add NaCl, immediately a white precipitate is formed here, right? So this reaction is super fast. You just took a solution, you added another time. So if I want to show you once again. So I told you that certain reactions are very fast, right? Super fast reactions, whereas certain reactions are very slow, right? But I have some examples for you. So let us see this reaction where we have taken simple AgNO3 solution in a test tube. You have seen that, and to that I will add certain amount of NaCl. Okay, now see, as soon as I added NaCl, immediately the reaction color has changed, right? It has become white in color. The precipitate has formed immediately. You might have done this reaction in your lab also many times, right? This is a test for chloride. But at the same time, rusting, as we have studied in electrochemistry, rusting is a chemical phenomena, right? It is a reaction, right? It is a chemical reaction, but it takes years and years for a substance or for a rod, iron rod, to get rusted. Why? Because this reaction is a slow reaction, whereas this is a fast reaction. I hope you are getting the difference in our environment, in our surrounding also. We see certain reactions very fast, certain reactions very slow. We just don't observe them, right? But after studying this chapter, every reaction you see, you will definitely able to find it out whether it is a fast reaction or a slow reaction. Okay, now let's move to the next thing, that is fine. Now let us start about the rate of a chemical reaction. Many times I have already told by this time that rate of a chemical reaction means speed of the reaction. How fast or how slow is the rate of the reaction, right? Let us see it in the words of chemistry now. Okay, So the speed of a reaction or the rate of a reaction can be defined as, how do we tell that the speed of the reaction has this much, or the speed of the reaction is this much? How do we define it? It is the change in the concentration divided by the change in time. Okay, so how do we tell about the speed of a vehicle or something? The distance covered by the time taken, or the change in distance by the change in time. Similarly, here we talk about the change in concentration of the reactants or products divided by the change in time. I hope you are getting this one. Now, to be more specific, it can be expressed in terms of the rate of decrease in the concentration of any one of the reactant, or the rate of increase in the concentration of any one of the product. So you know that in this, what happens in a chemical reaction, what happens? Suppose I have a reaction like this, right? So as the time progresses, the concentration of the reactant will decrease and the concentration of the product will increase, right? So with time, what will happen? The change of, if I'm talking in terms of reactant, with time the concentration of the reactant will decrease, right? And if I talk about in terms of the product, the concentration of the product will increase, right? And with respect to what time, in what time this change has taken place, that will give me the rate of the reaction. Now, very interestingly, we have two types of rate. One is your average rate and another is your instantaneous rate. You should be able by now, like, what is the difference between these two types of rate? So average rate is calculated in a certain time interval. For example, 5 seconds, 10 seconds, 1 minute, 24 hours, 50 minutes. In a certain time interval, you are calculating the rate of the reaction. Okay, that is called average rate. Then what is instantaneous rate? Instantaneous rate means, from the word itself, it is at a particular instant of time. Okay, so now if I go and ask Soumik sir, what is the rate of the reaction at this point of time? So whatever answer he will give me, that is my instantaneous rate. Okay, and if I go and so ask Soumik sir, till now you are already in the lab, you have been doing, so in the last 1 hour or in the last 30 minutes, what is the rate of the reaction? So when I'm asking them a time interval, in this particular interval, what is the rate of the reaction? That is my average rate. If I'm asking them that at this particular instant, now exactly at this point, what is the rate of the reaction? That is something called as instantaneous rate. Okay, now I'll show you how can we calculate both of them. Okay, now you see this is a graph. Can you see the graph and tell me that this, what is happening here? Here the concentration is decreasing, right? So that means this graph is with respect to a reactant, right? And here if I see the concentration is increasing, right? So that means this graph is with respect to a product. Okay, now whenever we calculate average rate, okay, we take a certain time interval, a bigger time interval. Whenever we calculate instantaneous rate, it is calculated from the slope of the graph. Okay, I'll explain you. So first let's talk about this graph, okay, where I have the concentration of the reactant. It is decreasing, right? Now if you see here, you can see that so if I check here, this at this point of time T1, okay, and I have this point of time T2, okay. So what is the change in concentration? This at T1 the concentration was R1, at T2 the concentration is R2. So with time the concentration has changed. So what is the average rate? So it is minus delta R by delta T is equal to minus R2 minus R1, the final concentration minus initial concentration. Now why I am putting this minus here? So for reactants, if you do not put minus, the rate will come as a negative quantity, okay, but rate should always be positive quantity. So to manage that, we put a negative sign. Okay, so final concentration will definitely be less than initial concentration because the rate is the concentration is decreasing. So final minus initial, you will get a negative quantity. So to satisfy that or to change that, we put a negative before the equation. Okay, now here this change that has happened, this change over this time interval will give me the rate of the reaction from T1 to T2. That is my average rate of the reaction in terms of reactant. Now if I talk about instantaneous rate, so at any point of time, that is at point T, what you can do is you can just draw a tangent in the graph you can just draw the tangent and calculate its slope. What is the slope of this tangent? That will give you the instantaneous rate. Now how do we represent average rate? With delta. How do we represent instantaneous rate? With dr by dt. So what is this? Dr by dt is equal to negative of the slope. Okay, negative of the slope. So now I am very clear. I hope this is very clear that whenever we have the rate of the reaction, average rate I want to calculate, it has to be in a certain time interval. For instantaneous rate, how do we calculate instantaneous rate? We calculate instantaneous rate by drawing a tangent and then calculating its slope. Okay, now let's talk in terms of product here. Product, what will happen? You can see the product concentration will increase with the time. So if I want to calculate the average rate in terms of product, so what you will do, you can see this is T1, this is T2, right? Here it is P1 and here it is P2. And if I just calculate the difference in the concentration of product by the difference in the time, you will get you will get delta P by delta T, or that is P2 minus P1 by T2 minus T1. Here I am not using any negative sign, because the final concentration will definitely be more than the P1, okay, and this term will be a positive quantity. And if I want to calculate at this particular instant of time, what is the rate of the reaction? So you have to draw a tangent and then you have to calculate the slope of that tangent, right? So that will be dp by dt is equal to slope of the reaction. Okay, so that is how we calculate the average rate and the instantaneous rate. Got it? Okay, now we will talk about something, that how do we express this reaction rate. Okay, so I'll tell you first. Let me give you an example. Yes, if I have a reaction like this, okay, so what is rate? Rate will be equal to what we studied in the definition of rate. Rate is something, the change in concentration of the reactant or the change in concentration of the product. So I can write rate is equal to, I can write like this, minus dA by dt, that is change in the concentration of one of the reactant. Rate can also be written as, I can write in terms of B, right? Or I can write in the terms of product also. So you can see here, since it is reactant, I am putting negative sign, but for the product one, I don't have to put any positive sign. I'll get dC by dt. Now can I equate all of them and write rate is equal to minus dA by dt, mine is equal to minus dB by dt, right, is equal to plus dC by dt. I can write like this, right? So this is how we express the rate of a reaction. This is the equation from where we will get questions or we have to solve this. Now just imagine I have a different case here. Sorry, yes, suppose I have like this, 2A plus B gives me 3C. Suppose the reaction is right like this. Then what will be the rate in terms of A? Rate is equal to minus dA by dt. Okay, it is not like this. Here you have to understand that this stoichiometric coefficient is there. So whenever you have any stoichiometric coefficient, that is divided here. Okay, clear? Now for B, what I will write? Rate will be equal to minus dB by dt. And remember always that with reactants we have to use negative sign, but with products we have to use positive sign. So rate for the C will be how much? Plus 1 by 3 dC by dt. Okay, this is done. Now if I want to write it together, how can I write? Rate will be equal to either minus 1 by 2 dA by dt, right, is equal to minus dB by dt, okay, is equal to plus 1 by 3 dC by dt. Yes, are we clear on this? If yes, please put a thumbs up, and we have understood how do we express the rate. Okay, this is from where questions can be expected. So now let us do some practice. Okay, so here I have the first reaction, or the first reaction given to me. I will be writing its rate. So what I can write here? Rate will be equal to, okay, minus of dHg by dt. Okay, concentration, change in the concentration of Hg divided by dt. The square brackets represent the concentration. Then that will be equal to minus of dCl2 by dt, and that will be equal to plus, here I have to put plus, dHgCl2 by dt. Clear? Any doubt here, students? I hope this is very clear. Very, very important, the first part from where numericals can be asked here. Okay, now let's try this one. Here you see some coefficient is there, right? 2Hi gives H2 plus I2. So how will I write? Rate is equal to minus, first of all minus 1 by 2, because this 2 is there, d of Hi by dt, right? Then I have plus d of H2 by dt, then I have plus d of I2 by dt. Clear? Similarly, can we try this one? This is very simple now. So I have minus, so first I'll write rate is equal to minus 1 by 5 d of Br minus by dt is equal to 1 d of BrO3 minus by dt, minus I forgot, sorry, minus I have to add, then I have equal to minus 1 by 6 of dH plus by dt. Okay, so I have added all this, Br minus I have written, BrO3 minus written, H plus is also written. Then I have plus 1 by 3 of dBr2 by dt, okay, is equal to plus 1 by 3 dH2O by dt, right? So this is the complete rate of the reaction. I'll just be aside, you can check once. Okay, I hope you are also writing with me. Clear? Fine. Now let's move to the next part. Okay, so now with this we will start the first quiz of this session. So as you know, if you are new, you might not be knowing, so we will be having 3 quiz rounds in this class, and the first quiz round has 5 questions. Okay, so you have to answer this, and if you want, you can put the answers in the comment section. If not, I want the final score you have to put in the comment section. Means in round 1, 5 out of 5, how much you got? 3 questions if you are doing correct, 3 out of 5, 4 questions if you are doing correct, 4 out of 5. Similarly, you can put the question numbers, okay, your scores. So let us see the first question here. So this is a fill in the blanks type question. The minus sign in the rate minus dA by dt indicates the dash in the concentration. Minus sign indicates dash in the concentration of the dash with time. Okay, the rate of a reaction is always dash quantity. The rate of the reaction increases with dash in concentration of the reactants. Okay, so let's see this. The minus sign in the rate minus dA by dt indicates the dash in the concentration of the dash. So minus shows that there is a decrease in the concentration. So I will have decrease here. I can eliminate these 2 options, right? Decrease in the concentration of what? Reactants concentration decreases, product concentration increases. So decrease in the concentration of the reactants. Here it is products. So I have only this option left, okay? But let's see the next one. The rate of the reaction has to be a positive quantity. That is why we put a negative sign here. So it is a positive quantity. The rate of the reaction increases with the increase in the concentration of the reactant. So this part we will see after studying the factors. Okay, so by now we can see that option number C is the correct answer. Okay, let's move to the second question. Okay, for the reaction A plus B gives you C plus D, the variation of the concentration of the reactant with time is given by the curve. So how does the reactant changes with the time of the reaction? I have just shown you the graph. If you see, okay, the reactant concentration decreases and the product concentration increases. So where there is decrease in concentration, if you see graph 1, it is decreasing and it is the graph of the reactant. So the answer here will be option number A. Okay, let's move to the third question. Nitrogen dioxide decomposes to nitric oxide and molecular oxygen as 2NO2 gives you 2NO plus O2. The concentration time data for the consumption of NO2 at 300 degrees Celsius are as follows. So you have been given time 0, 100, 200 and 300 seconds, and the concentration of NO2 is given at 0 seconds, at 100 seconds, at 200 seconds and at 300 seconds. So what we have to calculate? The average rate of the decomposition of NO2, average rate. So how do we calculate? Rate is equal to change in concentration by change in time, right? So you can take any time interval, that doesn't matter. But if you see this reaction, okay, so what I can write here? Rate is equal to, right, minus of 1 by 2 of dNO2 by dt, right, is equal to 1 by 2 of dNO by dt, right? So I have been given with which data? I have been given with NO2, so I'll just take that one. So I can write rate is equal to minus 1 by 2 of dNO2 by dt, right? So minus 1 by 2. What is the change in concentration of NO2? You can see, we'll just consider if this 100 seconds. So from 5.6 to 8. So I have 5.6 to 8.4, right? 5.6 minus 8.4 into 10 to the power of minus 3. So if I solve this, how much I'll get? 14 minus 6 will be somewhere 8, 7 minus 5 will be somewhere 2. I'll have 2 minus, okay, and you have divided by 100 also here, right? So into 10 to the power of minus 5. So that will give me minus 1.4 into 10 to the power of minus 5, right? So which is the nearest answer? I will get here, here I did a mistake. See, this one will give me negative here. So negative will come positive. Rate is never negative. So rate is always positive. So I'll get plus 1.3, which is nearest answer, 1.3 into 10 to the power of minus 5. Okay. Next, question number 4. For the reaction 2x plus 3y gives 4z, the rate of the reaction may be represented as. So let's see here. 2x plus 3y plus 4z. Okay. So how can I write? Rate will be equal to minus 1 by 2 dx by dt is equal to minus 1 by 3 dy by dt is equal to plus 1 by 4 dz by dt, right? So if this is the answer, which option is correct? I can see with first option I have here, there is no negative in the first option, right? So I can eliminate this one. Second option, I have negative here, I have negative here, I have positive here. This seems to be correct. Let's see the other two options. Here there is no negative, so that is why this is wrong. Here also no negative, this is wrong. Okay, so B is the correct answer. So 4 questions are completed. Last question of round 1 is there. I hope all of you are ready and you have got correct answers till now. Moving to the 5th question. For the reaction N2 plus 3H2 gives 2NH3, how are the rate of the reaction expressions interrelated dH2 and by dt and dNH3 by dt? What is the relation between these two? Okay, we are talking about H2 and NH3, right? So I can write rate is equal to minus 1 by 3 of dH2 by dt, and I can also write rate is equal to 1 by 2 plus 1 by 2 of dNH3 by dt. Okay, now if I equate both of them, so what I'll get here? Minus 1 by 3 of dH2 by dt is equal to plus 1 by 2 of dNH3 by dt. Clear? So now what will be the answer here? Minus 1 by 3 dH2 by dt, and here we'll have plus 1 by 2 dNH3 by dt. Okay, so that is option number A here. Clear? Okay. Now moving to question, now we have already discussed the 5 questions, okay, and you can just put down your, what I'll say, you have put down your scores in the comment section. If not, please quickly put it, and we are now moving to the second part. Now after having a clear understanding of what exactly is the rate of the reaction, what are the types of the reactions, types of rate of the reactions, we have average rate and instantaneous rate. Now do you remember Somik sir? Somik sir, or the Dr. Somik sir, has told us that there are certain factors by which I will try to increase increase the rate of the reaction and produce the antidote in 24 hours, right? So we can change the it is not the rate of the reaction is not constant. We can change the speed of the reactions, and what are the factors for that? The first factor is concentration. The second factor is temperature, and the third factor is catalyst. Okay, we will be studying about each of these factors in detail, and in today's class we are going to cover the first factor, that is concentration. Okay, let's move here. So when studying about concentration, what all topics we have? The first thing we'll study is dependence of rate on concentration. So Soumik sir told us that concentration is a factor, but is it if I increase the concentration, rate will increase, or if I increase the concentration, rate will decrease? So how it is related, that we will see. Second, rate expression and rate constant. What is this rate expression? What is this rate constant? Third, order of the reaction, and fourth, we will study about molecularity of the reaction. Okay, 4 topics we are going to cover under concentration. Okay, let's move about dependence on the rate of the reaction. Now see, the rate of a chemical reaction at a given temperature may depend on the concentration of one or more reactants and the products. So just now also when we have defined rate as the change in concentration by change in time, right? So the rate is definitely dependent on concentration. Okay, that is clear to us. Now the representation of the rate of the reaction in terms of the concentration of the reactants is known as rate law. Now something that is very special about rate law, we'll study about this in detail. So now I am saying that suppose a reaction is there, R gives me P. So what does we have learned till now? Rate is proportional to the concentration of the reactants. Okay. Now we will be deriving in the next few slides a relation, an expression, a formula from this one, and that formula is called as rate law. Okay, so it is also called as rate equation or rate expression. Okay, this rate law is also called as rate equation or expression. Now we'll go in detail here. Rate generally increases when the concentration increases. Okay, generally or most I can say commonly we find that if the concentration increases, the rate of the reaction will also increase. Okay. Now we'll talk in detail about this rate expression and rate constant. Okay. So now see, suppose I have this reaction. What is rate law? Rate law tells you the relation between the rate and the concentration of reactants, not products. Okay, only with the reactants. So what I can write here? I can write, let me take a different color. I can write rate is proportional to concentration of A to the power of X, concentration of B to the power of Y. Now what is this X and Y, ma'am? We will talk about that in few time. Okay, so what is X and what is Y, we'll talk. But now remember, X may or may not be equal, or it may not be equal to A, that is your coefficient. Okay, it may or may not be equal. Similarly, Y may be equal or may not be equal to the stoichiometric coefficient. Okay, so this X and Y may sometimes in some reactions may be equal to their stoichiometric coefficients. In some other reactions it may not be equal, right? Now there is a proportionality. To remove a proportionality, what we do? To remove the proportionality, we introduce a constant, right? So I can write rate is equal to K into A to the power of X and B to the power of Y. Right? Rate is equal to K into A to the power of X and B to the power of Y. Now this X, this K is nothing but rate constant. Okay, and this total thing is nothing but rate law. You can call it as rate law, rate expression or rate equation. Okay, this total thing is called as rate law, rate expression or rate equation. This K is called as rate constant. Now what is this X and Y? X and Y are, we'll talk about that. So first let us see some important definition. This form of equation, so I can write here one more thing, just I'll add here, one second. Yeah, I can add here that, so I can write rate is equal to also minus dr by dt, change in concentration of the reactant. is equal to this one. So this form of equation is called as differential equation, where K is what? K is the proportionality constant or rate constant. Okay. Next, the equation which relates, this is very important, the rate of the reaction to the concentration of the reactants. Okay, it is nothing to do with the product. We are just worried with the concentration of the reactant. When rate and the reactant concentration is related, it is called as rate law or rate expression, which we have already seen. Now this is the proper definition of rate law, which can be also asked in the exam. So see it properly. Rate law is the expression, this rate law is an expression in which the rate is given in terms of molar concentration of the reactants. Molar concentration of the reactants. This square bracket shows you molarity, right? So there are different ways of representing concentration. We have mole fraction, molarity, molality, normality, but in rate law what we take? Molarity. Okay, the molar concentration of the reactants with each term raised to some power. This x and y are some power, which may or may not be equal to the stoichiometric coefficient of the reacting species in a balanced chemical reaction. This x and y may or may not be equal to the stoichiometric coefficients, right? That is your total rate expression. Clear? Now let us move forward and talk about this particular reaction. Now if you see, I'll give an example. Suppose we have a reaction 2NO plus O2 gives 2NO2. Okay, this is a reaction. Now let us understand something here. See, when we have, I have initial concentration of NO is 0.3, okay, and initial concentration of O2 is also 0.3, okay. Now what I did is, I kept O2 concentration same, okay. I have not changed anything with O2 concentration, but I have doubled the concentration of NO. You see, from 0.3 to 0.6, okay. First I went and I took 2 test tubes, okay. Here I have, just a minute, I'll do it in a better way so that we can properly imagine it, okay. So we have one beaker, okay. So here you have NO, okay, and here you have O2. Okay, now what he did is O2 concentration was same, and now you added some more amount of NO. You doubled the concentration of NO in the second trial. First trial we have taken equal amount of NO and equal amount of O2 in the first case. Now again I did this reaction. Okay, what I did, I just added O2 and I added twice of NO. Means the rate of O2 concentration is constant, but the rate of the concentration of NO is double. So what I observe, if you see here from 0, the rate, what is the change in the rate? From 0.096 to it became almost 0.384, okay. So how much times it has increased? So if I see that if I am doubling this one, see, if I am doubling this one here, the rate has become 4 times. You can see the rate has become 4 times, 4 6 are 24, 38, this has become 4 times, right. So whenever I will double the concentration of NO, or NO, the rate is becoming 2 times, right. Now let us assume a scenario where you have taken a test tube. Here O2 concentration is doubled, but NO is still the same. Means how much NO was here, it is there, that is I have taken same amount of NO and O2 concentration is doubled. So where I can observe that, let's see here, you have in these 2 scenario, you see, okay, in these 2 reactions what I have done, I have kept NO constant 0.3, okay, but I have doubled the concentration of O2. Now when that is happening, what is happening to the rate? When O2 concentration is doubled, the rate has become 2 times, right. But when NO concentration was doubled, the rate has become 4 times. That means I can say that if I am changing the concentration of NO double, means I am just making it double, the rate is becoming 4 times. But if I am changing the concentration of O2 to double, if I am increasing the O2 concentration to double, the O2 concentration just doubles. So what that means, that I can write the reaction like this. See, rate is equal to K into NO to the power of X, O2 to the power of Y. Right. Now here this X and Y you have to understand. See, when you are doubling this X, when you are doubling this NO, how many times the rate is changing? It is becoming 4 times, right? Means 2 times it is becoming double. So that means X value will be 2. Okay. If you increase the rate or the concentration of NO rate is becoming 4 times, right? So it is becoming double, so it is to the power of 2. And here if you, it is directly proportional. If O2 is double, rate is double, so that is directly proportional. So here I will have this Y value as 1. Okay, so this is the final equation. Clear? Now this tells me that now if Soumik sir wants to prepare the antidote, if he have this equation, now he can know that if I want to increase the rate of the reaction, then how much NO, if I double the NO, the reaction rate will become double. If I double O2, the rate reaction will not double, it will just become double. Here it will become 4 times. So how the concentration can be changed so that the rate of the reaction is affected? That is something called as the order of the reaction, about which we'll study in the next slide. I hope you're getting. Now here in this particular reaction, if you see, the X and Y are equal to the stoichiometric coefficient, right? Here it is 2, here it is also 2, here it is 1, here it is also 1. But there are certain other reactions. If you see, CHCl3 plus Cl2 gives you CCl4 plus HCl. Here the reaction is KCHCl3 Cl2 to the power of 1 by 2. So here you see the stoichiometric coefficient and the equations are different. Similarly, you have this reaction CH3COO C2H5 plus H2O gives CH3COH plus C2H5OH. Here also you see that for this one there is 1, for water it is 0. Okay, so these numbers, how do we find out? These numbers are determined experimentally. How we have done an experiment here, right? I have taken NO and O2, then I have doubled the concentration of NO. I am seeing the reaction is becoming 4 times. That means with respect to NO, it is a second order reaction. And here if I am doubling the O2, the rate is also becoming double. That means with respect to O2, it is a first order reaction, right? So that is something is called as the order of the reaction. For any law, for rate law, for any reaction cannot be predicted by merely looking at the balanced chemical equation. Okay, this rate law cannot be predicted by looking at the equation. What we have to do, it has to be determined experimentally. You have to change the concentration and you have to see the change in the rate of the reaction, then only we can find the rate law of a reaction. Okay, it cannot be determined theoretically. Clear? Now if I go to the next part, that is the order of a reaction. So what exactly is order of a reaction? Now see, let me just tell you, we have understood in a layman language, in a very simple terms, I am telling you what is the order of the reaction. Remember it. Now see, I told that when the concentration changes or when concentration increases, rate will increase, right? But how much increase? How does it increase? If I am doubling the concentration, is the rate is also becoming double? If I am doubling the concentration, if the rate is becoming 4 times? If I am doubling the concentration, rate is becoming 3 times? How much change is happening when the concentration is changed? How much rate is changing when the concentration is changed? That is what is given by the order of the reaction. Okay, so what I'll tell here, see, order of a reaction tells about how much change in concentration, sorry, how much change in rate takes place with the change in concentration. Okay, so just now we have given, so how do I write rate for any reaction? For example, I have a reaction A plus B plus B gives me C plus DD, and the rate of this reaction can be written as A to the power of X and B to the power of Y. So the sum of this reaction, the sum of the X and Y is called the order of the reaction. Okay, sum of the reaction or sum of these powers X plus Y will give you the order of the reaction. Now let's see here some important points. The sum of the powers of the concentration terms in the rate law expression is called the order of the chemical reaction. So for this particular reaction, what is the order? For this particular chemical reaction, the order is X plus Y, where X and Y are the coefficients of are the powers of A and B respectively. Next, order of a reaction can be 0, 1, 2, 3 and even a fraction. This is very important. We have just seen in the previous slide. Here I can see that here it was half, right? You have see a half was there, here 0 was there. So order of a reaction can be 0, 1, 2, 3 and even a fraction. Next, the reaction taking place in one step are called as elementary reactions, and the reactions that takes place in multiple steps are called as complex reactions. Okay, now why are we discussing this here? I'll tell you again after some time. So if a reaction is taking place in one step, we call those type of reactions as elementary reactions. If a reaction is taking place in multiple steps, we call it as a complex reactions. Okay, so order is clear. What does order will tell me? Order will tell me if I am changing the concentration, how much change the rate will happen. Okay, so let us give some example here. See, if the order of a reaction is 0, that means what? There is no change in rate with concentration. Okay, if the order is 0, that means it is not, the concentration is not affected, or in that case, in that type of reactions, the rate is not affected by the concentration. That's the first thing. Second, if it is first order reaction, that means the rate is proportional to concentration. Means if you triple the concentration, rate will also triple. If you double the concentration, rate will also double. If you decrease the concentration, rate will also decrease. Next, if rate is second order, if order is a second order reaction, then what will happen? Rate will be proportional to concentration the square. That means if you are doubling the concentration, rate will become 4 times. If you are tripling the concentration, rate will become 9 times. If you are quadruple, means you are making it 4 times, the rate will become 16 times. So that it will become 2 times of that, right? That is your second order reaction. Okay, we'll study about these 3 order in detail. So just don't worry, I'll explain. But now, for now, you have to understand that I have told, or Dr. Somik sir has told us that if I change the concentration, rate will increase, definitely. But how much? If you double the concentration, whether the rate will become double or whether the rate will become quadruple, means 4 times it will increase or it will increase 2 times, that we can decide only from the order of the reaction. I hope I am very clear here. Let me just explain you once again, because this is something very, very important. Rate of a reaction is directly affected by the concentration. But if you double the concentration, how much time the rate will change? Will that also become double? Will that become 4 times? Will that become 8 times? That can be answered only by the order of the reaction. Okay, so that is something that you have to understand. Now let's move to another term, that is unit of rate constant. Okay, now we have seen, so I have written for example, I have a rate like this is equal to a to the power of n. Okay, suppose this is a rate reaction or a rate law for a particular reaction like this. Okay, I have written the rate law like this. Then what is the K I can write? K will be equal to rate divided by a to the power of n. Right? Now what is rate concentration? Just a minute. Now, what is the unit of rate? So if you see, the unit of rate is what? Rate is concentration by time, right? Concentration was given in terms of molarity. So I can write rate is concentration, that is mole liter inverse by time, right? That is the unit of rate. And here you have again concentration mole liter inverse divide to the power of n. So if I just equate this, what I will get? Moles to the power of 1 minus n, okay, liters to the power of, you can see this is goes up, it becomes n minus 1 second inverse. Okay, so this is the unit of K. What is n here? N is the order of the reaction. Okay, it can be 0 order, first order, second order, half order, any order, right? So how can I write this one? Just a minute. Yes, so you can see this table. Okay, I'll just hide, I have hidden it. Okay, one second. Yeah, I'll write this formula above somewhere. So what is the unit of K? Unit of K is equal to moles to the power of 1 minus 1 liter to the power of n minus 1 second inverse. Now let's try this here. if the reaction is a zero order reaction, I can substitute in the place of N0. So what I'll get? Mole, liter inverse, second inverse, right? If it is a first order reaction, substitute 1 here, this will become mole to the power of 0, that is 1. Liter 1 minus 1 to the power of 0, I'll get only second inverse. Second order reaction, 1 minus 2, so it will become moles to the power of minus 1. Liter 2 minus 1, so liter and then second inverse. This is the unit here, right? Fine. Now let's move to the next topic, that is molecularity of a reaction. Molecularity is very simple. Number of species reacting in a reaction. If the reaction is happening, how many species are reacting there, that is the molecularity of a reaction. For example, you can see NH4NO2 gives you N2 plus H2O. So this is only one molecule is there which is reacting. So this is a unimolecular reaction. Here if you see 2HI gives H2 plus I2, here 2 molecules are reacting, so it is a bimolecular reaction. Next, if you see 2NO plus O2, 3 molecules are reacting, so it is a trimolecular reaction. So what is molecularity? The number of reacting species taking part in an elementary reaction which must collide simultaneously in order to bring about a chemical reaction is called as molecularity of a reaction. Number of species that should react such that the product is formed. See, if you take so many reactants can collide with each other, but when these collisions results in the reaction, a product formation takes place. At that time, how many reactants molecules have collided, that gives you the molecularity of a reaction. Now generally molecularity of a reaction is not more than 3. Okay, we have very difficult to find reactions with molecularity greater than 3. Now what is the reason for that? Very simple. It is not always possible for more than 3 molecules to react, to collide with a particular energy, with a particular orientation to give you a product, right? If normal collision is happening, no product is formed, that we cannot calculate as a reaction. We cannot consider that as a reaction. If a reaction is happening, collision takes place between the reactant molecules and product formation takes place. In that case only we will call it as a reaction, and in that case only we will get the molecularity of a reaction. So more than 3 molecules colliding and giving you product is very less. Okay. Next, let's move to the next part, that is so now there's a very important question, which step controls the rate of overall reaction? See, I have discussed something called as complex reaction. Complex reaction has many steps, it occurs in more than one step. Then which step will you will consider as the as that this step is determining the rate of the reaction? So always remember, it is the slowest step. The overall rate of the reaction is controlled by the slowest step of the reaction, and it is also called as rate determining step. Okay, so let us give you an example. H2O2 gives you H2O plus O2. Now this reaction takes place in 2 steps. In the first step, H2O2 and I minus react to give you H2O plus IO minus, and in the second step, H2O2 reacts with this IO minus to give you H2O plus O2. Now this is a slow step, this is a fast step. So the rate of this reaction will depend on this particular step. Okay, so this particular step, whatever is the order of this particular step, that will be the order of the whole reaction, right? So that is what is given here. Now we will talk about the difference between order of a reaction and molecularity of a reaction. Very, very important. Now what is order of a reaction? If I talk about the definition, it is the sum of the powers of the concentration terms in the rate law expression, right? What is molecularity? The number of species reacting in a balanced chemical equation. Okay. Nature, it has to be determined experimentally. Okay, the rate law is determined experimentally, so order is also determined experimentally. But this can be determined theoretically. Just by seeing the reaction you can tell what is the molecularity, but just by seeing the reaction you cannot say what is the order of the reaction. Next, possible values, it can be 0, fraction or an integer, but it is always 1, 2 or 3. It is rarely more than 3, but it cannot be 0 or fractional. Okay, at least 2 molecules has to collide, at least 1 molecule has to collide to give you a product, right? So 1 is the minimum value of molecularity. Next, applicability, it is applicable in both elementary and complex reactions. Okay, you can have order for an elementary reaction, for a complex reaction also, but molecularity, it is applicable only to elementary reaction. Why we cannot apply it to complex reactions, because in complex reactions there are a number of steps, right? There is not a single step, so we cannot find for like what is the overall molecularity of this reaction. So molecularity of a reaction is always applicable to elementary reactions. Next, given by the order for complex reactions, what happens? It is given by the order of the slowest step, and here it has no meaning for the overall complex reaction, only valid for each elementary step. Now if a complex reaction has 5 steps, then each step will have a molecularity value, right? But overall we don't have any molecularity for a complex reactions. Okay, then we have how it is obtained. It is obtained from the rate law, it is obtained from the balanced equation. Okay, so this was the difference, and now it's time to do some quiz. Okay, so here I have 11 questions for all of you. You have to put the comments, your scores in the comment section. So by now what we have studied here: what is a rate law, how do we express, what is the order of a reaction, what is molecularity of a reaction, right? So let's do some questions from this. The first thing, the decomposition of dimethyl ether is a fractional order reaction. The rate of the reaction is given by K into P to the power of CH3CO CH3 whole 3 by 2. P represents here pressure. Okay, if a gas is there, instead of molarity we use the term pressure. If the pressure is measured in bar and time in minutes, then what are the units of the rate constant? Very good question. So how do we find rate constant? You have been bar minute inverse, bar square minute inverse, bar minute inverse, bar minus 1 by 2 minute inverse, bar minus 1 by 2 minute inverse, bar square minute inverse, and you can see all the options. So let's do. We have to find first what is the unit of rate and rate constant. Now see, I have rate is equal to what? K into pressure of CH3CO CH3 to the power of 3 by 2, right? This is the formula we have. Now what I have here, I can write rate unit. Rate is always what? Rate is always change in pressure, dP by dt, it will be always dP by dt, and change in pressure I can write bar minute inverse. Okay, rate unit will be bar minute inverse. So bar minute inverse, these two I can cancel. Now rate constant. So in this equation what will be K formula? Rate by, okay, rate by, I hope it is visible, rate by pressure of right, this 3 by 2, sorry. Okay, now let's put the unit here. What is the unit of rate? Bar minute inverse, right? And what is the unit of pressure? It is bar to the power of 3 by 2, right? So 1 minus 3 by 2, it will become minus 1 by 2. I'll get bar minus 1 by 2 minute inverse. Okay, so I will get bar minus 2 minute inverse here. So option number B. Okay, let's see the next question. You have to match the rate law given in column 1 with the dimensions of rate constant given in column 2 and mark the appropriate choice. Okay, so this is a zero order reaction, right? K, this is zero order reaction. For zero order reaction, what is the unit? If you remember, I'll just write the equation. K unit formula is moles 1 minus n liter n minus 1 second inverse. So if it is a zero order reaction, I will get mole liter inverse second inverse, which is the correct match here. So A has to be 1. I can eliminate these two options. Okay, let's see B. Now here H2O and I minus, sum of the power here is 1, here is 1. So rate is a second order. So I'll get 1 minus 2, 2 minus 1 means minus 1, and here I'll get 2. Mole minus 1, liter 1 second inverse. B is also correct. B is 2. B is also 2 here. Let's see 3 by 2 here. So if I substitute 3 by 2, so what I'll get? Moles 1 minus 3 by 2 liter 3 by 2 minus 1 second inverse. So it will become mole, right, minus 1 by 2 liter, I have 1 by 2 second inverse. So is it matching correctly? No, C has to be 4. So C has to be 4. So my answer is option number D here. Okay, Let's move to the next question. The unit of rate constant for the reaction 2H2 plus 2NO gives 2H2O plus N2, which has a rate of this one is unit of rate constant. Okay, so what is the order of this reaction? Here 2x sum of the powers, right? So what is order of the reaction is 3. 2 plus 1 is 3. Then what will be the unit of K? Moles to the power of 1 minus n, liter to the power of n minus 1, second inverse. So I'll substitute here moles, 1 minus 3 is minus 2, liter is 2, second inverse. That is this one, option number C here, right? Let's see question number 4. In a reaction A plus 2B products, the molecularity of the reaction is, molecularity is the number of species reacting. So here 2 and here 1, so molecularity will be 3, that is option number A. So you see molecularity we can easily predict by seeing the reaction itself. Next we'll go to among the following statements, the true statement is the order of a reaction changes with the temperature. The molecularity and the order of the reaction are always equal. The molecularity and the order of the reaction can be determined experimentally, or only the order and not the molecularity of a reaction can be determined experimentally. What is the first statement saying? The order of a reaction changes with temperature. We haven't studied anything like that, right? So this is a wrong statement. Molecularity and order of the reaction are always equal. No, I told you it may or may not be equal. So this is also wrong. Molecularity and order of the reaction can be determined experimentally. No, molecularity can be just determined by seeing the reaction, but for order we need to find experimentally. So yes, this is also wrong. Only the order and not the molecularity can be determined experimentally. That is absolutely correct. That is option number D here. Next, for a chemical reaction, the molecularity may be 0 or fractional order. The order is always equal to molecularity. The order is always different from molecularity. The order and the molecularity may be same or different. See, molecularity of a reaction is never 0 or fractional. Okay, it is always 1, 2 or 3, and 3 is the highest value. Rarely it goes more than 3. Order is always equal to the molecularity. No, order is always different from the molecularity. It may or may not be same. So that is why order of the reaction and molecularity may be same or different. Now let's see the next one. In a multiple step reaction, the overall rate of the reaction is, the overall rate of the reaction is equal to the rate of the slowest step. Yes, equal to the rate of the fastest step, equal to the average rate, equal to the last step. So I have told you it always determines by the slowest step, and the slowest step is also called as rate determining step. Next, we'll see the reaction between H2 and ICl occurs in the following steps. The reaction intermediate in the reaction is. So what is the intermediate? Intermediate means something which is formed between the reaction. It is not in the starting, it is not in the final product. It is formed in the reaction and it is consumed in the reaction. So if you see the first one, here I can see HI. So if I add these two reaction, okay, first one and second one, HI and HI will get cancelled. I'll get H2 plus 2ICl gives me I2. One second, will give me I2 plus 2HCl. Right now, something you can see HI. HI is formed in the first reaction and in the second step it is consumed. So the intermediate in this reaction is HI, that is option number B here. Let's see the next question. For a reaction 2NO plus 2H2 gives N2 plus 2H2O, the possible mechanism is. So to find out the possible mechanism, the rate of the overall reaction depends on the slowest step. So it has to depend on this one. So what is here N2 and H2? So rate will depend on N2O2 and H2. It will not depend only on N2. This is wrong. N2O2, here also H2 is not there. Here the square we have not discussed anything. Here no 2 is there. So that is why option number B here. Now see, this is an elementary reaction. Means this reaction itself is one step. Okay, so in this elementary reactions, the stoichiometric coefficients will be equal to the power of the concentration terms in the rate law expression. Right, so that is why here it is 1. So here also it is 1. Here 2. It is here also 2. Okay. Next, we'll move to 10th question. Select the intermediate in the following reaction mechanism. Intermediate. So if I just add this reaction, O3 gives me O2 plus O, Here I have O plus O3 gives me 2O2. Okay, so I can add these two, so you can see I'll get 2O3 gives me 3O2. Right, this is the reaction. So what is there? Something which is produced in between and consumed, that is oxygen. So B is the intermediate formed here. Now let's see the next question. The reaction A plus 2B plus C gives you Z occurs by the following mechanism. Okay, the rate law of for this reaction is, now rate law will depend on the slowest step, so that is something which is the slowest step. But now if you see here, X is an intermediate, right? X is not there in the final reaction. So rate cannot depend on X, or in the rate law we cannot write X because it is not there in the final reaction. So rate is only proportional to the concentration of C. Okay, so that is why option number A here. Okay, AB will not be there because in this step there is no AB. Here there is no Z. This is also not there. This is also not there. X is something which is an intermediate formed. C is something which is the final product. It is there in this one also. So the rate will depend on C. Okay, so now we will go to the next part. So now that we have solved these questions, we have practiced, I have given you so many knowledge about chemical kinetics. Let's go back to our scenario where our JJ Mam, beloved JJ Mam is ill. She needs this antidote to within 24 hours to save her life, right? Do you remember the scenario that I have given you in the starting of the class? So now I am with Soumik sir in the ICMR or the lab, and I have these questions for Soumik sir. Sir, how much time is it required to prepare the antidote? We have this 24 hours deadline, okay, right? The clock is ticking, the time is running out, we don't have enough time. So how much time is required? And the second most important question is how much amount of antidote can be prepared, because we need a particular doses, right? It is not just whatever amount we prepared we can give. So how much amount that is prepared can be that is required, can we prepare that much amount in this given period of time or not? Right? So these are the questions. So now Soumik sir says me that your questions, ma'am, can be answered by something called as integrated rate equations. Okay, so integrated rate equations tells us how much quantity of the product can be prepared in what amount of time, how much the reaction can be completed in a given interval of time. Okay, so you have to now watch my next video on chemical kinetics to get answers to these questions. First question, was the antidote finally prepared or not? Second question, how to calculate how much antidote is prepared in how much time? Okay, and the third very important, most important question, that is, could we say JJ Mam or not? Okay, so these three questions I'll be answering in the next session, so you have to stick around and watch my next video at any cost if you love our favorite JJ Mam. Okay, so now let's move to the homework time. So since I have already given you so many knowledge today, I have already discussed what is a rate of a reaction, how to calculate the rate law, order of a reaction, molecularity of a reaction. So many things we have studied. So till the next lecture comes, till all your answers are all your questions are answered in the next session, you have to answer these three questions that I have given in the homework. And what you have to do, you have to put down the answers in the comment section, and I will be recognizing and I'll be applauding all the students who have shown the participation in the homework section, as well as also put down your scores out of total 11 plus 5, 16 questions were there in the today's session. So how many questions you answered, please put down in the comment section your scores. Okay, very important. So students, that's all in this video, and do watch next video. It is going to be super exciting and super suspense and thriller that we are going to uncover what happened to JJ Mam, right? So that's all in this video, students. Thank you so much for watching, and all the best. Keep learning and keep smiling.